Hi, this is Just Nessery, and this is the third week of Poli-Sci 509, the linear model. And this week we're going to talk about what an ordinary least squares regression means in a geometric sense. And I don't necessarily mean how to plot y against x on a scatter plot. That is a very useful skill. What I mean is how to understand what OLS regression is doing in a deep sense from a geometric perspective. And one of the immediate ways you'll know we're not going to do the typical scatterplot thing is the way we're going to interpret variable vectors. So let me start off by just writing down a couple of variable vectors here. So suppose we've got two vectors, x1 with two observations 5, 2, and x2 with two observations 1, 4. Now these are variable column vectors. So x1 might be our first independent variable of interest, x2 might be our second independent variable of interest. And what we're going to do is we're going to plot these vectors in observation space. So I'm going to pull up let's try that again. I'm going to pull up a graph here, and I'm going to say that the x-axis is observation 1 and the y-axis is observation 2. What that means is you're used to seeing graphs where, say, y is on the y-axis and x is on the x-axis, and those correspond to variables. In this case, the variables are actually going to be vectors in this space defined by observations. What do I mean by that? So let me just show you by drawing some hash marks on here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Let's consider the x1 vector here. If I was going to plot the x1 vector in this space, I would mark off, let's see, 5 on observation 1 and 2 on observation 2, and I'd make a little dot there. And then I'd come in here and draw a vector. There we go. And if I write down this here is x1. This is the x1 variable as represented in observation space. The first observation has a value for x1 of 5. And the second observation has a value for x1 of 2. So this is a data set with two observations in it. It's kind of a small data set. It's a toy data set, in fact. Everything I'm going to say applies to larger dimensional data spaces, but you'll see why we're sticking with two observations for the time being a little later in the program, so to speak. Observation 2, or I'm sorry, x2, variable 2, would be at location, let's see, 1, 1, 2, 3, 4, so right there. So if I come in here and draw a vector, there we go. I can write in x2. There's the location of variable x2 in this two-dimensional space. So I've got two vectors in two observational space. Each vector corresponds to a variable. Now suppose I wanted to add these two vectors, which is sort of what I'm getting at down here. Well, you know from a couple of weeks ago how to add vectors numerically. So if I just say x1 plus x2, you know that what we're going to do is take each of these column vectors and add them element by element. So 5 plus 1 is 6, and 2 plus 4 is 6, so x1 plus x2 is 6. Now, watch this. If I come over here and plot x1 plus x2 on this graph, so let's say 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 here. That would go right there. Right there. There we go. If I were to graph this, it would have the location indicated by the point, and I could actually even put in a vector right there. There we go. This is x1 plus x2. But you might notice that x1 plus x2 is actually the sum of these two vectors graphically as well as numerically. What do I mean by that? If I take x1 right here, and there's its tail, there's its head, if I were to just drag it up to x2 right here, like just like that, what you'd see is that the x1 plus x2 point is located at exactly the place where if I had started with x2 at the point or head of x2 and put the tail of x1 right there, that would lead me to the point x1 plus x2. The same would go if I started at the head of x1 and put the tail of x2 at the end of it. So if I came over here and said, okay, there's x2 right there, x2 is also that vector right there, I still reach the same point. So this is all just kind of a way of saying that when you add two vectors, you don't just add them numerically. There's a graphical interpretation. Specifically, adding two vectors is the equivalent of putting two vectors head to tail in a graphical sense. That's equivalent to adding vectors, oops, not is, in an arithmetical sense, or in an arithmetic sense. Arithmetic sense. Oops, E. So there you go. There's your first fact about adding vectors. Okay, so that's adding vectors. Now what about subtracting them? Well, subtracting them, as it turns out, is conceptually very similar to adding them. So what I'm going to do here is do another axis right there. See if I can, there we go. Subtracting them, instead of putting them head to tail in the intended direction, you kind of put them head to tail in the opposite direction that the vector was originally intended to go. What do I mean by that? Well, let's come down here and look at x1 minus x2. So x1 minus x2. Now x1 is 5, 2, x1 is 1, 4. So x1 minus x2 would be 4, negative 2. There we go. Now, I've got negative numbers, at least in the y dimension, so I'm going to need to extend that downward a little bit there. Now let me draw in some hash marks. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. Okay, so again, plotting x1 and x2. x1 is 5, 2, so 1, 2, 3, 4, 5, 1, 2. There it is. Put in that vector there. There's x1. X2 is 1, 4. So I'm just going to go straight there. 1, 1, 2, 3, 4. Huh, nice spacing. If I was going to subtract these vectors, what I would do is I would take, here's the x2 vector, here's the x1 vector. I would take this x2 vector right here, let's see if I can select the x2 vector. There we go. Let me copy that, come over here, paste it. If I was going to add them, I'd put it up here. I'd put them head to tail. If I'm going to subtract it, I kind of reverse the direction. So I put it tail to head, as it were. And that, if I've done this correctly, should give me a point of 4, negative 2. Now, 1, 2, 3, 4, negative 1, 2. And you can see my spacing is a bit off there, but that's x2, or x1, sorry. x1 minus x2. And this is observation 1, this is observation 2. So subtracting vectors is very similar to adding them. You just sort of go in the opposite direction. We actually don't do a great deal of matrix subtraction, or I'm sorry, vector subtraction in what we do, but it's nice to see that connection there just in case it ever becomes relevant for you. So that's, I'm sad to say, kind of the easy part of what we're going to talk about today. Now let me start getting into the more meaningful, for one thing, but also the little bit more difficult material. So as we've just seen, vectors do have a graphical interpretation. vectors can also be thought of as forming a subspace in the real number hypercube K. So the first question you might be asking yourself is, what did I just say? What is the real number hypercube K? Well, all we mean by that is just the space defined by placing real number lines at right angles, K real number lines at right angles to each other to form a space. So this is one that you've seen a lot probably. Oops, I'll leave the two arrows there. This is the Cartesian plane. Okay, that is R2, because here's the first real number line 1 and here's the first real number line 1, and we've put those two spaces together at right angles to form a real number space 2. Here's, oh, come on, actually let me just, well, do I have room? Let's see. Oh, jeez. Curse you. There we go. Okay, so if I label these, there's Z, and there's X, and there's Y, and you got to imagine Y kind of shooting out of your screen as a third dimension. This here is R3. It's the space defined by 3 real number lines, all perpendicular to each other. You can see all the angles here are right angle, and then if I could draw it in here, that'd be a right angle. And each one of those lines is a real number line. R1 is this friendly guy. You probably have seen this person many times, at least since you've been in Algebra 1. That's R1. So all we mean by this is there's some space created by the real number line, or a number of real number lines placed at right angles to each other. And vectors form a subspace of this space where K is the number of vectors that you have. So let me give you a sense of what I mean here. Okay. So suppose I have two vectors. I'm going to call this vector x, and it's equal to 1, 0. And I've got a second vector, we'll call it y, and this vector is equal to 0, 1. This pair of vectors forms a subspace in R2, because there are two vectors, and this is what it would look like. Let's say, whoops, let's say this is the point 1, 0, and this is the point 0, 1. That would make this vector here x. Sometimes we notate the vector with a little hat there, and here's vector y. This is a vector space, or a subspace of R2. It only goes out to 1, 0 and 0, 1, and that's it. This is the kind of space that you might be familiar with. You can see that it's got nice right angles here, like you're kind of used to with the Cartesian plotting plane, so it's a friendly subspace. But there are lots of different possible subspaces, some of which are not so friendly. So let me just partition off some space here. Let me give you two other vectors that are going to be a little less friendly. So here's x, 3, 2, and y equals 1, 4. Now, what would a subspace created by these two vectors look like? Well, I'm just going to plot them out. So I'm just going to specify an origin point here and say 1, 2, 3, 1, 2. And if I come up to my vector line, there we go. That is x. Y is 1, 4, so that's in 1, 2, 3, 4. Oh God, my spacing is awful. Yeah, okay, good enough. There's y. This is also a subspace. You can see the angle between these two vectors is very obviously not a right angle, but this subspace is related to this subspace here, the first subspace we drew. These two things are related to each other, this here and this here. The reason why they're related is because it's going to turn out that we can represent points in the space of R2 using either coordinate systems, and in some sense they're going to be equivalent to each other. So the takeaway point of this is that any collection of vectors you have can in principle form a subspace inside of the space of Rk, where k is the number of vectors. Now one thing that you well, actually, let's just skip right down to this point, and then we'll come back to what I was about to say. So one point I wanted to make here is that any point in the space of k linearly independent column vectors out of a matrix x n by k, so k is the number of columns, so we've got k column vectors, can be expressed as a combination of the column vectors in X. Now, what do I mean by that? Well, I mean the following thing. So let's take as an example this vector space that we started off with, 1, 0, and 0, 1. I'm going to take this and see if I can grab, well, I'll just create a new space here. There we go. Here's a nice space. And I'm going to draw the x and y vectors in this space. So if I come in, I'm going to come down here and say, okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Drawing x and y, so x is 1, 0, y is 0, 1. I can draw those vectors in this space like so. There's x, and there's y. There's x, and there's y. Okay. Any point in this space, so this is R2 space right here, can be represented as a linear combination of these two vectors. Let me just give you an example. Let's take a random point, 4, 2. This is point 4, comma 2. I can represent that point as 4x plus 2y. And here I'm just going to put these hats on these vectors so that you don't get confused with variables later. There we go. So I can do that for any point in this space that I want to, going out to infinity or negative infinity in any direction. So all I have to do is take, okay, I need 4x vectors to get out to the 4 and 2 to get to the 2 on the y, and that's it. Now, what's a little tricky about this is I can also do this for the crazier vectors 3, 2, and 1, 4. So without belaboring this too much, let me take a little graph here. I'm going to draw in 1, 2, 3, 4, 5, 6. Whoops. Crap. There we go. 1, 2, 3, 4, 5, 6. Okay, so now let's take those crazier vectors. That's 3, 2, and 1, 4. So here's 1, 2, 3, 2. So 1, 2, 3, 2, and 1. Oops. What was the other one? 1, 4. 1, 2, 3, 4. Okay, so there are my two vectors. This is x and this is y. And now my original point here was 4, 2. So I've got 1, 2, 3, 4, 1, 2. There we go. Now, how could I reach this point in x and y? Well, what I could do is basically stretch or shrink these x and y vectors to get to that point. And it's what I'm telling you is that with these two vectors, I can still reach any point in R2, which this is R2, by stretching and shrinking x and y. The real question is, how far do I have to shrink them to get there? And it's a little bit hard to see, although graphically you can kind of get a sense that what we're going to do is stretch x out a little bit and then tack on a negative version of y that reaches downward, and we're going to shorten it a lot too. It actually turns out that there's a fairly easy way to figure out exactly how much we need to stretch or shorten x and y. So x is equal to 3, 2. and y is equal to 1, 4. And what we want to do is, okay, say, well, I'm going to stretch x by an amount a. So that's a multiplier. So I could maybe double it by 2x. Or I could put it in half by a half x. Or I could go in the opposite direction with like negative x. I want to stretch or shrink x, and then I want to stretch or shrink y by a factor b, and I want to get to the point 4, 2. So I've got a times 3, 2, plus b times 1, 4 equals 4, 2. Now I can write that in a way that's going to be very helpful to me. 3, 2, 1, 4 times a, b equals 4, 2. This is a system of linear equations like we did on the first week of class. That I just wrote and this expression over here are equivalent in a mathematical sense. And you can see that by doing the matrix multiplication and figuring out what equations you get by result. But we've already covered that, so I'm not going to belabor it too much. So what we want to do is solve this equation for a, b to figure out how much we need to stretch and shrink x and y. So as you might remember from the first and second weeks of class, what we're going to do is pre-multiply both sides of this equation by the inverse of 3, 1, 2, 4. Any matrix times its inverse is equal to I, which is the matrix form of 1. So what we get is AB on the left-hand side, and on the right-hand side we get 3, 1, 2, 4 inverse times 4, 2. And that's a problem that one could solve by hand, but it's just easier to come over to RStudio and do it. So here is my matrix A, and you see I've already entered in all the right stuff for A. Oh, whoops. So I'm going to come in there. A, 3, 1, 2, 4, just like on the screen. And xy is what I've called the resultant vector there. I'm not sure why I called it that. I just did. So there's xy equals 4, 2. That's the point we're trying to reach. And so now if I take A inverse times xy, what I get is 1.4.2. So going back to my other thing here, A, B equals 1.4 negative 0.2. Is that negative? Yes, it is, negative 0.2. So what this means, going back to my graph, is that what I would do to get to this point using x and y is I would stretch x by about 1.5. That's about right? About somewhere in here maybe. And that's going to be my new x vector stretched out. And then I would take y and use 0.2 of it, so shrink it down by 1/5 to 1/5 of its size and go in the opposite direction. So what I've got is that's 1.4x and negative 0.2y. And I can get to that point. And I can repeat that process for any point in R2 and get there. So what I'm kind of alluding to here is that this crazy x and y vector, which are at some weird acute angle here, not 90 degrees, they can effectively serve as a plotting plane in the same way that the friendly 1, 0, 0, 1 vectors that you're used to can also serve as a plotting plane. Normally we're used to saying, something x and something y, right? 2x plus, or x equals 2, or some point is 4, 2, right? All we're saying is that it's 4x plus 2y. Well, we can just as easily say that it's 1.4x negative 0.2y if by x and y we mean these weird kind of acute vectors. Alright, now what I want to do is get to the graphical connection to OLS regression. So we've set up a lot of facts in abstract mathematical terms. Now we're going to pay off on that in OLS. So what I've written here is that in a linear regression, the columns of x n by k, so x n by k is the matrix of independent variables, form a space in the real number hypercube of dimension k, where k is the number of independent variables that you have, including the constant term. This space is a subspace of the n-dimensional space defined by observations. Bing! Okay, here we go. So I'm going to start with a real basic space. There we go. Okay, this is a 3 observation space. So this is like observation 1, and this is like observation 2, and this is like observation 3. So I've got 3 observations, okay? Now suppose I have 2 independent variables that I'm measuring. So I've got 3 data points and 2 variables, okay? Let me put these variables into this observation space. Here's one of them. There's the other one of them. So we'll call this one x1 and we'll call that one x2. Now you can imagine these 2 variables jutting out into the 3-dimensional space created by observations. So we've got here n equals 3 observations, but only k equals 2, so only 2 variables. What does that mean? Well, that means that the subspace created by the independent variables is going to be 2-dimensional. That is to say, it's going to be a plane. And that plane is going to float in the 3-dimensional space created by observations. So look at this graph here. You can sort of see x1 and x2 are forming a plane, right? If I were to, oh boy, here we go. Let's see if Professor Esri can draw. I already know the answer to that is no, but we'll give her a shot anyway. So if I take x2 and sort of move it along and create a grid. So I'm going to use a different color here. Actually, I'm going to use gray. Gray is good. Where's my cursor? So if I just sort of sketch in these lines here, this is all I'm doing is just replicating x2. I'm moving it along the x1, the axis created by x1. Okay. And now what I'm going to do is move x1 along the axis created by x2. So here's that. Just like that. And there we go. You can see that what I've got is a plane floating in 3-dimensional space. You can sort of think about it as a piece of paper like this one floating in the 3-dimensional space that we inhabit as a part of our lives. Same thing exists on this graph I've got here. It's just that in this case the 3 dimensions aren't height, width, and depth. They're observation 1, observation 2, and observation 3. That's the 3-dimensional version. Now you might be able to see this a little bit more easily if we consider a 2 observation. Oops, there you go. Oh. Bah. Go down here. So let me I'm going to move this down a little bit. So let me create a 2-dimensional space like that. And so now what I've got is 2 observations. Well, I don't want the gray anymore. Observation 1 and observation 2. And let's say I have 1 independent variable, just 1. So there we go. I'll call that x. Now I've got a 1-dimensional space floating in 2-dimensional space. A 1-dimensional space is a line. A 2-dimensional space is a plane. So I've got a line in a plane. That's just a more colloquial way of saying what I said up here. The space formed by the columns of your independent variable matrix is a subspace of the space created by observations. And what this should make clear to you is why we need n to be bigger than k when we run regressions, which is to say why we need more observations than we have independent variables. So continuing with the 2 observation case, so here's observation 1, observation 2 again. If I have one variable, that's kind of fine, right? I've got a nice subspace. If I've got two independent variables, now I can reach any point in observation space with these two variables. And actually, this is a way of saying that my data set is going to be kind of perfectly determined. I'm going to be able to perfectly predict it in a sense of the word. If I start throwing in even more variables, here's x3, now I actually don't even have, I have more variables than I have observations, so I don't really need that third variable to do any prediction in this space. It's superfluous. In fact, I could predict x3 with x1 and x2. x1 and x3 is no longer linearly independent from x1 and x2 in a sense. So that's why we need more observations than we have variables, and that's even going to become more clear as we proceed with the demonstration and I start showing you what linear regression is doing in this subspace. All right, what is OLS doing here? Well, what OLS is doing is the following. So you remember from last week that we know that something is done to the y variable using that the dependent variable, that is, using the matrix of independent variables to produce predictions y hat. And in particular, we know that y equals x beta hat, right? And we know that we get beta hat from, I'm sorry, y hat equals x beta hat. So the prediction of y is x beta hat. And we know that we get beta hat by taking, this is the formula you should have tattooed on your arm, x transpose x inverse x transpose y, right? So that means that y hat predictions are given by, I'm just taking this x times this beta, x transpose x inverse x transpose y. So we know that something is done to the y variable using the x matrix to produce predictions y, and that something is defined by this matrix here. So just store that for a second. Furthermore, we know that a prediction plus the estimated error term adds up by definition to the observed value of the dependent variable. So what that means is that these two vectors added together need to add up to, or need to form some kind of triangle in vector space. So if I've got, again, two observations, observation 1 and observation 2, here is, let's say, my dependent variable. I'm going to move this around a little bit, actually. Let's try this. Call that y. Okay. I know that my prediction and my u have to add up in some way to y. So, for example, what might be the case is I've got, here's a prediction vector right here. This is going to be y hat. That's the variable corresponding to the predictions I generate out of an ordinary least squares regression. U is going to have to add up to y, so u hat's going to have to be that guy there. So if I can move this down a little bit, move this guy down here. Let me move this guy right there. These two things have to add up to y. Furthermore, they have to be at right angles to each other. You notice that I intuitively drew this at a right angle. They have to be at right angles to each other. Well, how do we know that? Well, the reason we know that is because if they're not at right angles to each other, u hat would not be as short as it could be. And one of the key facts we learned from last week's lecture is that the point of OLS, or the goal, what OLS does is pick beta hat, that is to say pick y hat, that makes the estimated error terms as small as they possibly can be. So imagine, for example, that y hat was actually out here. something crazy, right? So this is going to call this y hat prime, something bad. That would imply a u hat prime to add up, to add up to y, we would need u hat prime to be this, u hat prime, and you can see that's really, really long. So in essence, y and u hat need to be right angles at each other? Well, if y hat and u hat are not perpendicular, then the length of u hat's length is not minimized. But we know that OLS determines the beta hat and y hat that results in minimized length of u hat. So it's got to be the case that those things are at right angles. Otherwise, we have a problem. Incidentally, I don't want to go into this too much, but the length of, well, no, I'll just skip that. Actually, we'll get back to that later. So linear regression represents a projection of the y vector onto the space defined by x and minus k. Well, what do I mean by that? Let me go back up to this diagram right here. I'm going to pull this out. I'm going to copy that. I'm going to come down here and paste it. Let me get some of the, I'll get rid of the extraneous extra vectors here. Actually, I think I can erase them. Yeah, there we go. Let's get rid of those. Okay, so here's y hat, u hat, and y. Okay. Y is this vector right here. Y hat is equal to x times beta hat. We know that, right? So that means that y hat is a stretching or shrinking of the x vector. So the x vector might be something like this. In this case, x is a line, so we know that there's only one x variable in a two-dimensional space. And beta hat is what shrinks that line, that vector, to minimize u hat. If you think about it, we'll just stop right there for a second. What I want to talk a little bit more about is what we mean by projection. So what do I mean by a projection? Well, imagine there are lots of different ways of thinking about this, but I'm going to start with a kind of intuitive one and then get to a little more technical one. So here's my diagram here, and imagine that I've got some kind of light source. Do I have any yellow? Yeah, here we go. Here's the sun. It's shining. That sun is projecting light down on y, and x is kind of like the ground in this scenario, and y is kind of like a pole shooting up out of the ground in some ways, right? So it's shooting up into the sky. Y hat is like the shadow that the y pole casts onto the ground formed by x. That's why it's sometimes called a projection, because it's literally a projection of this imaginary light source onto x. U hat is the distance from the tip of the shadow to the edge of the pole floating in space, which is another way of saying it's the part of y that can't be represented by a line on the ground. In this case, a line in x, in the space defined by x. So it is what ordinary least squares regression is doing is creating this projection. Now, a more technical way of thinking about this is to say there's a part of y, the dependent variable, that can be explained by x, the independent variable, but there's a part of it that can't be. And what ordinary least squares regression does is find the part of y, get as close to the tip of y as you can by moving in the space in the linear space defined by x. In that case, in this case, that point is right about here. That's as close as I can get to the tip of y right here, but just by moving linearly in x space. That's not all the way to y, right? There's this additional distance to travel, u hat, but it's as close as I can possibly get. So x beta hat is that point in the x subspace that's closest to the point of y in the larger subspace. So x here, you notice, is a subspace, or is a space in R1. The observation space is larger; it's a space in R2. X beta hat is the point in this R1 line that's as close as I can get to the y vector in R2 space. So that's what that is. It might also be helpful to see this kind of mathematically. So as I mentioned before, here's y hat, here's beta hat, and y hat equals x quantity x transpose x inverse x transpose y, right? Well, so y hat equals x transpose x inverse x transpose y. This part right here, oops, try that again. This bit right here is a matrix called Px, or the projection matrix for the space defined by x. What dimension is Px? Well, x is, let's see, x is n by k, right? So this is n by k. This is transpose, that's k by n, so that conforms. That's n by k. This whole inverse is going to be also k by k. And then this here is going to be k by n. So this P matrix is n by n. And what it does is it takes a vector, like y, as input, and it projects that vector onto the space defined by x. So it tells you how much of any vector input can be represented in x space, or how close can you get to that vector in x space. So another way of writing this equation over here is that y hat equals px y. These two things mean the same thing. Px is just a shortening of this longer matrix equation. All right, so what this leads us to is our next fact, orthogonality. X beta hat and u hat are orthogonal. By orthogonal, that word, we mean a bunch of different things, all of which are equivalent to each other. The first thing we mean is that the angle between x beta hat and u hat is 90 degrees. And I hopefully convinced you of that up here when I showed you this little diagram demonstrating that if that were not so, the length of u hat would be too long. It would be longer than it needed to be, and therefore u hat would not be minimized as ordinarily squares, as we showed last week, does. There's actually a little proof of that I can show you pretty quickly. So I'm going to take this diagram here real quick. So we've got, let's just say we've got some y, and we've got some x beta, oh, no, and we've got some x beta, and we've got some u. So this is y, x beta hat, and u hat. And this line here is a perpendicular from the intersection of y u hat to x beta, and that perpendicular forms a 90-degree angle, like so. Okay, so what is the length of u hat? Well, by the Pythagorean theorem, we know that if this height here, that perpendicular has length a, we know that u hat squared equals a squared plus x beta hat minus j squared, where j is that length right there, j, from there to there. So all I've done is I've said, okay, this length here has to be whatever this length is, that's a squared, plus this length squared, which is x beta hat, which goes all the way out to there, minus whatever length j is. So all I'm doing is the usual Pythagorean theorem deal, where I say the opposite side squared plus the adjacent side squared equals the hypotenuse squared, as long as we have a right angle here, which we do. So that's the length of u squared. Now, what value for j minimizes the length of u? So actually, I could rewrite this as u hat. The length of u hat equals the square root of a squared plus x beta hat minus j quantity squared. There we go. So what value for j is going to minimize, or what value for x beta hat, I'm sorry, is going to minimize this equation? Well, I think just trivially, without doing any calculus or anything, I think it's going to have to be x beta hat equals j. How do we know that? Well, this is squared, so negative values are not going to help us. They're not going to shorten this vector. So basically what we want to get this vector down to is as small a number as we can get, which is going to be 0. That's going to be true whenever j is exactly equal to x beta hat. So I think it's the case that we want to get x beta hat equal to j, that is to say u hat to be at a right angle, in order to make u hat as small as it can be. So it's just like a real simple proof-like thing using the Pythagorean theorem of this first point, if you weren't convinced before. That statement is equivalent to the statement that u hat cannot be represented by vectors in x. That point comes out of the following demonstration. So remember that px is what projects a vector y onto the x space. But by definition, u hat is at right angles to x beta, right? So what that means is if we try to project u hat into the space defined by x beta, it would be like asking what kind of shadow a pole facing straight up casts at noon. So imagine here's our little space here. And imagine I've got a y. Whoops, I'm going to put a point on that. I've got a y here, and I've got an x beta. There's an x beta hat. And I've got a u hat. Now remember, we got the sun right about here, asking what part of u hat lies in this x beta space. How close can I get to the point of u hat on x space? And the answer is I can't get very close at all. Imagine moving u hat down to the origin. Oops. So I've just moved u hat down to the origin. How could I move along this space x beta to get closer to u hat? Well, I couldn't get any closer than the origin. That is to say, I couldn't get any closer than beta hat equals 0, right? If I make a negative beta, I'm going to move out here. I'm going to get further away. If I make a positive beta, I'm going to move out here and get further away. The closest I can get is 0. So u cannot be represented by vectors in x, and we've incidentally just also shown 4, a regression of x on u hat is going to give you a beta of 0. Equivalent to all of these statements is that x times x transpose x negative 1 x transpose u hat equals 0, or alternatively px u hat equals 0. There is no projection of u hat onto x. Now, one thing I want to emphasize to you is that these are all properties of estimates, not of the data generating process of the real world. We're not talking about u and x beta here. It is not necessarily true that if there's a real data generating process that's linear, x beta, and a real error term u, that those two things will necessarily be orthogonal. What I'm telling you is if you're in a regression and you fit y hat and you fit u hat, the fit of u hat will, if you regress y hat on u hat, you will get 0 correlation by definition, no matter what the data generating process is, period. That's my point. So if I go over into RStudio here, and I just pick an x and a y, and I run those, and then I model, I run a linear model of y on x, generate predictions y hat, I'm going to call that model.pred, and then get residuals from that model, which is just going to be y minus y hat, or model.pred, so there we go. And then I try to predict the residuals with the fitted y hat, so I'm going to basically run a regression, a scatterplot version of a regression of residuals on the predictions. There it is right there. Look what happens. I get what amounts to a 0 correlation, no correlation at all, which makes perfect sense given what I just said. And if I run a formal regression here, you can see that the coefficient on that regression is as close to 0 as I can pretty much get without it being 0 in machine language. You know, 9 or negative 3.2 times 10 to the negative 16th, that's 0. So one last point about this. You know, everything I've just said holds in higher than two-dimensional space. All my diagrams have been in two-dimensional space because they're easier to draw. But all of these 4 points, that x beta hat u is 90 degrees and all that, that all holds in as large as the data set can get. A 1,000 data point data set will, all these things will be just as true as they are in a 2 observation data set. So just to give you a real quick sense of what this might look like. So so let me take a 3-dimensional space. So this is observation 3, observation 1, observation 2. So imagine I've got 2 vectors, and for ease of exposition, I'm just going to put those 2 vectors in sort of a real flat space. So it's, you know, I'm going to put x1 here, and I'm going to put x2 there. This is going to be x1. It's going to be x2. And imagine y is kind of shooting upward like that. So this is like y. If I was going to try to represent y in the space defined by x1, x2, I would probably just visually, it would look something like that. And there'd be a u hat defined there. This would be x beta hat right there, or y hat. And these 2 things would be at right angles, like so. And what I've done is I've basically said, how close can I get to y on the plane defined by x1, x2? If I ran the residuals from this regression against y hat, I would get 0 correlation, just as I got in the 2-dimensional matrix. So nothing special, there's no trick in this 2-dimensional case. It always works. And I hope you saw that from the RStudio example. So going back to RStudio here, you can see that this data set has 100 observations in it. So y equals 2x plus 3 plus a normal distribution centered on 0 with a standard deviation of 1. That's a 100-dimensional space. And even in that 100-dimensional space, when I try to run a linear model predicting y hat, or predicting u hat with y hat, I got nothing, even in that 100-dimensional space. The reason I'm telling you this is for several reasons. You may have already heard some of them, but if not, you'll hear them again. You may have heard at some point, and if you haven't yet, you will eventually hear, that it can be a problem for the error term u to be correlated with the regressor's x. There are lots of cases where that might be a problem. And some people's initial reaction is to say, oh, well, I should check for that. So I'm going to run this regression. I'm going to y equals x beta. I'm going to run that. And then I'm going to estimate the residuals out of that. So like y minus y hat equals u hat. Okay, I got my estimates for residuals. Okay, now what I'm going to do is I'm going to see if x predicts u hat. The answer will always, no matter how bad or good your regression is, it will always be no. And that's not true because of any property of the world. That's a property of OLS. OLS is designed to work that way. So that's what you're going to get if you do that, and you shouldn't use that as a diagnostic tool. Okay. So let's talk a little bit about variance decomposition in the sum of squares. So all right, recall that x transpose x, this should be x transpose x inverse. Go up there. One. Yeah, there we go. X transpose inverse x transpose equals the projection matrix Px projects any n by 1 vector into the space defined by x. There first is an equivalent residual matrix Mx. Let's talk about that a little bit. So Mx is I, n by n, minus P, which we've already discovered is n by n. What the projection matrix does is give us the residuals. So if, for example, I were to take a vector y and pre-multiply it by mx, what I would get is u hat. So mxy plus pxy equals y again. I've got the residuals from y and then the fitted values for y, so I've got u hat plus y hat. That's got to add up to y for reasons we've already established. And as I just mentioned, the Pythagorean theorem says that x beta squared plus u squared equals y squared. So what is this thing that I've got here? Well, this double set of bars with something inside of it is called the Euclidean norm. Oops. Euclidean norm. And that's just a way of denoting the length of a vector. So what we're saying is that the length of x beta hat squared plus the length of u hat squared has to add up to y squared. So y hat squared plus u hat squared equals y squared. Okay, so we've been over that. Hopefully you know that part. What these facts together give us is information about the degree to which x can explain the variance of y. Okay, what do I mean by that? Well, I'm going to start by just writing the length of y squared equals the length of x beta hat squared plus the length of u squared. Okay, u hat squared, sorry. Okay, this is equivalent to y transpose y. Why is that the case? Well, that is the case because the Euclidean norm of some vector x equals the sum of all the components of x squared and then the square root of the sum. Again, this is implied by the Pythagorean theorem. If I take every part of x, square it, and then add them up and take the square root, I will get the length of x. So imagine here's one part of x, x1. Here's another part of x, x2. There's the total length of x, a squared plus b squared equals c squared. That's all we're doing. There's no real trick here. So y transpose y, we learned in the first and second weeks of class, is equal to the sum of squares of some vector. So the Euclidean norm of y squared is just y transpose y. It's this squared. So that's going to equal x beta hat transpose x beta hat plus u hat transpose u hat. Okay. This is sometimes called the total sum of squares. This is the explained sum of squares, and this is the residual sum of squares. So what we mean by this is that there's some degree of variation in y that can be explained with x. And that variation is representable by the sum of squares of x. In fact, if y has a mean of 0, then the variance of y equals the sum from I of 1 to n of y minus mu y I squared, like so. That's the variance of y. Well, if mu y equals 0, this equals the sum of I equals 1 to n yi squared, or y transpose y. So if in a special case where you've just transformed y to have the mean equals 0, the total sum of squares is the variance of y. So the ESS is the proportion of the variance of y, or the degree of variability in y, that can be explained by movement in the x-plane. And the RSS is that which remains, the part of the variance or variability in y that can't be explained by x. This identity, TSS equals ESS plus RSS, is often summarized in the R-squared statistic, which you've probably heard about in your previous classes. R squared is the explained sum of squares divided by the total sum of squares, or colloquially, the proportion of variation in a dependent variable y that is explained by x. And you'll notice that r squared has to lie inside of 0 and 1, and that's true because these are all positive quantities. U hat transpose u hat. There we go. U hat transpose u hat is a positive quantity. It's a sum of squares. This is a positive quantity. It's a sum of squares. It adds up to a positive quantity, which is the sum of squares, which implies that this cannot be any bigger than this. If it were, u hat transpose u hat would have to be negative, and that's not possible. So ESS divided by the largest that ESS can get is TSS. So the largest it can get is 1. The smallest it can get is 0 for the exact same reason. If this were less than 0, that well, that's just not possible because the sum of squares is not less than 0. So the smallest this can get is 0, so the smallest r squared can get is 0. So we've got a nice summary statistic telling us, in short, how much we can explain the variability in y by a linear projection of x. All right. Now what I'm going to do is talk about some facts about projection matrices, and some of these will become more important as we talk, further our discussions of OLS. But for now, there's sort of interesting curiosities, which you have to trust me, they'll become important later. So the first is that Px, or the projection matrix of x, is idempotent. Idempotent is a big word that means that it's a matrix that, when it's multiplied by itself, gives you itself back. So here it is right here. Px equals Px. Why is this true intuitively? Well, all right, so let's think about this for a second. So here is a little observation 1, observation 2. Here's a little diagram, and here is some variable x, and here is some variable y. And if I were going to project y onto x, I would get something like this. So that is the projection pxy, and then that's going to leave me the residual vector here, mxy, like so. Now, what would be true if I tried to, what would happen, rather, if I tried to take pxy and project it onto x? This is a little bit like asking, if a shadow could cast a shadow, what shadow would it cast? It's a little Zen Cohen go along with your ordinary least squares regression. The answer is it would just cast itself because it's already the component of y that lies in x. You're already, anytime you multiply by a px matrix, you're locking yourself into the space defined by x. So any vector that's already in the space defined by x is by definition representable by itself in x. Now that's an intuitive explanation as best I can give it, but you'll also formally prove that for homework. Mx is idempotent as well, and it's that this fact is true intuitively for a similar reason to the one above. So remember that mx tells you the portion of some variable y that can't be projected onto x. So here's mxy right here in this diagram. mxy is like asking this is a little less it's a little easier, harder to explain intuitively. But you're asking what component is left or is not representable in x of some vector y, right? So this is the portion of y not representable in x. And then we're asking what portion of that is not representable in x? Well, the answer has to be all of it. So anytime you've multiplied by mx, doing that again is like, sort of the inverse of projecting a projection. You're just going to get the same thing back again. But if you don't believe me, we're going to prove that for homework as well, so perhaps you'll get it that way. mxpx is not just a bad punk band, it's also 0. mxpx equals 0, which equals pxmx. Why is that fact true intuitively? Well, if you consider again the meaning of px and mx up here, what you'll see is that what you're asking is, if I take pxy, say, for example, what's the portion of y representable in x? So I've got pxy, the portion of y representable in x, okay? Then I say mxpxy, what portion of the above is not representable in x? Well, the answer has to be none of it, because pxy is only the part of y representable in x. So none of that part is not representable in x. That's what we made it to be. So mxpxy has to give you back nothing, because you've in essence constructed something that doesn't exist by default. But we're going to prove that fact for homework as well. Now I've given you a bunch of proofs for homework, so it would be nice if I showed you how one of those would proceed. So here's another fact. Px transpose equals px, and mx transpose equals mx. Now I'm going to actually let you do one of these for homework. I'm going to let you do I'm going to let you do mx. Yeah, I'm going to let you do mx for homework. So I'm going to let you do this one here for homework. But this one I'm going to do for you right now. So let's just start with px equals px prime. Now a way of writing that longhand is x transpose x inverse x transpose equals px transpose. So this whole thing, x transpose x inverse x transpose, the whole thing transposed. So this is just going to be a bunch of applications of rules of matrix algebra that I taught you a couple of weeks ago. So what I'm going to do is start on the right-hand side and just try to make it look like the left-hand side with rules. Now, this right here is a matrix transposed. So what I'm going to do is I'm going to say, okay, I'm going to call this here A and this here B. And we know that AB transpose equals B transpose A transpose. So this is going to enable me to write X transpose transpose, or X, times X transpose X inverse transpose. So the transpose of a transpose is itself again. That's what I've done here. So this is B, and then this is A transpose. Okay, so far so good. Now I'm just going to do that same thing again. I'm going to call that A, and I'm going to call that B. I'm going to use the same rule again. So what I'm going to get out is equals X transpose X inverse transpose X transpose. Okay. Now, rule we learned a couple days ago. I guess it was a couple weeks ago now. A inverse transpose equals A transpose inverse. It's a rule of matrix operations. And I'm going to apply that right here to switch out these two superscripts. So I'm going to be able to say X quantity, X transpose X transpose inverse X transpose. Now, what's X transpose X transpose? Well, by this rule, it's just X transpose X again. Inverse X transpose. That is that. Proof complete. So that's what a proof looks like. That's one little example of it. And you should be able to play around with the rules of matrix operations to prove all of these things. And none of them are especially deep, or there's no like, oh, magic move. None of these are Nash equilibrium type proofs. These are fairly simple proofs that you can get just by sort of doing like I did, putting both things on one thing on one side of an equation, the other thing on the other side of an equation, just messing around with them until they look the same. That's pretty much a winning strategy for all of these proofs. All right, finally, consider x equals x1, x2. So this is what's called a partitioned matrix. So what I've done is I've said, okay, this x is like x1, x2, x3, blah blah blah, xk, right? It's a collection of each one of these as a column vector. What I've done is I've said, okay, collect some of these column vectors into one matrix, call it x sub 1, and collect all the rest into another matrix, call it x sub 2. So we can write that this is like x1, x2. So this is like n by k1, and this is n by k2. So I've just broken this matrix into a set of two column vectors. What we can show here is that P1, Px. Now P1 is the projection matrix for x1, for this matrix right here. P1, Px, where Px is the projection matrix for all of x. Alright, so P1 is the projection matrix for x, Px is the projection matrix, I'm sorry, P1 is the projection matrix for x1, Px is the projection matrix for the entire matrix X here. So what we want to show is that P1 Px equals Px P1 equals P1. Let's start with that fact right there. What we're basically saying here is that if we project, we first take the projection onto the entire space of X, and then we take the projection of that projection onto the space of 1, what we have left is just what's on 1. So let me try to give you a visual explanation for this, and then I'll give you a formal mathematical proof of it. So what I'm going to do is take a three-dimensional space like this, and I'm going to label some stuff here. I'm going to say this is x1, x2, and y. Okay, so y is a vector that juts out into this space. should I take that back? So this is observation 1, observation 2, observation 3. This is y. Here we go. Get your head in the game, Justin. This is x1, and this is x2. Okay, so if we take the projection of y onto x, so in other words, first thing we're going to do is take pxy. What we're going to get is some vector down here that looks like this, right? Something like that. The shadow cast by y onto the plane defined by x1, x2. So I'll call that pxy. Now, let's take pxy and project that, let's just say, onto x1. What are we going to have then? Well, what I want is the portion of this vector that's representable on that line space right there. In other words, something like this. In other words, I'm going to get the same thing I would have gotten if I had just directly projected y onto x1 only. So it's a little hard to talk about that intuitively, but in so much that we can, what we're saying is when we look at the portion of y that's representable on the entire x space, and then take a portion of that that's representable on just the x1 part of the space, we might as well just ask what part of y is representable on the x1 space. And the same thing is true if we go in the other direction. Well, I should say, actually, let me just say it like this. It doesn't matter which one we project onto first. We can do P1 PX or PX P1. Either way, we're going to end up with just the portion of y representable by x1, or representable on x1, rather. So that's the informal talking it through idea. It's a little bit rough, though, so let's maybe try another tactic and look at a formal proof. So what I want to show is that Px P1 equals P1 Px, and that all of this equals P1. So what I'm going to do is the same thing I did last time, is just write out this these definitions and see if I can make them equal each other. Okay. So I'm actually going to start with this bit right here. Here you. No, I take that back. I'm actually going to start with this bit right here. So what is P1? Well, P1, so do Px here, P1 is x1 times x1 transpose x1 quantity inverse x1 transpose, right? This is Px Px times, this is just the longhand definition of P1. Now what I want to do is say, okay, what is Px x1? Well, Px x1 is the portion of x1 that's representable in x space. What portion of x1 is representable in x space? All of it. So this just becomes x1, x1 transpose x1 inverse x1 transpose, or P1. So I can show that this equals this. That's what I've just done. Now I could, if I wanted to, do the same thing for this part. All I need to do is write, all right, well, let's see, x1, no, erase, x1 transpose x1 inverse x1 transpose px, right? I've just translated that into its longhand format. And then what I would want to know is, all right, what is x1 transpose px? Well, by the rules of transposition, that's px, wait a minute. Right. So that is px transpose x1 quantity transpose, right? I haven't done anything wrong there. All I'm just saying is that, like, A, B, transpose equals B transpose A transpose. So there's B transpose A transpose. So this whole thing, transpose again, has to be that. So what's PX transpose? Well, earlier we noted the theorem that PX transpose equals PX. So we can rewrite that as PX x1, quantity transpose. What's PX x1? We already decided up here it's x1. So we get x1 transpose, x1 transpose. So now we can then take that and substitute it in right there. And we're going to get x1 transpose x1 inverse x1 transpose, which equals P1, proof complete. So it's not really that complicated to show that both of these things equal P1 in a formal sense, but I hope that you have at least a little bit of an intuitive sense of it. And in case you don't, at least you'll have to formally prove this proposition right here in a way similar to the one that I just demonstrated. Okay, so why did I go through that? Well, you know, I like it, but that's not really the real reason. It allows us to state a theorem which it turns out is extremely important to ordinary least squares regression, and it's implicit in many of the things that we do quasi-unthinkingly. That theorem is the Frisch-Wall-Level theorem. The Frisch-Wall-Level theorem says the following. Consider two regressions. Y equals x beta hat plus u hat, right? That's just the usual regression. And now imagine, oh, this is slightly malwritten. No, there we go. Now consider an alternative regression, m1y equals m1x2 beta 2 hat plus residuals. And so what I'm saying here is, imagine what we do is we take the components of a data set and we run y against x1 and then get the residuals out of that regression. Then we regress x1 or x2 on x1 and get the residuals out of that regression. Then we model the residuals from the first regression against the residuals from the second regression and get another whole model. The Frisch-Wall-Level theorem says the estimates of beta 2 from this regression are the same as the estimates of beta 2 in the original regression. What did I just do there? Okay, what am I saying? Here's what I'm saying. If I've got a whole bunch of variables, what I can do is run them all individually as separate regressions, or I can run them all in one gigantic grand regression, and either way I'm going to get the same results. Now you might be saying to yourself, well, there's this thing called spurious correlation, and I'm really concerned about how, I don't want to just run y on a single x variable, because if I do that, there might be this other x2 variable that's spuriously correlated with x1, and so that's going to mess up my estimate of how x1 affects y. Well, the Frisch-Wall-Level theorem says, well, what you should do, or what you could do, one thing you could do is just run a regression of y on x1 and x2. Another thing you could do is you could run a regression of y on x1, predict the residuals, run a regression of x2 on x1, predict the residuals, and then do a third model of the residuals against the residuals. And that regression is going to give you an estimate of the effect of x2 on y that would be the same as if you'd run the giant regression. Alright, so that's my best attempt to talk it through. I think there's one application that's going to make it crystal clear how this really works. What I want to do is do a formal proof of the FWL theorem, just to show you that mathematically what I'm saying is correct. And then we'll move on to a substantive, more informal demonstration in RStudio. So here's the Frisch-Wall-Level theorem. So what I'm going to do is run a regression on m1y using m1x2, which is regression 2 in the statement above. So the definition of that, or what that regression is, recall the formula you should have tattooed on your arm at this point, is x transpose x inverse x transpose y. This right here gives you beta hat, right? So what I'm going to do is I'm going to say, okay, well, beta 2 hat from this partition vector up here is equal to m1 x2 transpose m1 x2 inverse m1 x2 transpose m1y. Okay, what did I just do there? Well, what I've done is I've said, okay, the role of x will be played by m1 x2. m1 x2 is the residuals of a regression predicting x2 using, x1. So in R, this would be like LM x2 squiggle x1, and then predict the residuals out of that to get m1 x2. That bunch of residuals is going to be our x variable here. So we take x transpose x inverse x transpose y. Now the role of y right here will be played by the residuals of a regression LM, let's try that again, LM y on x1. So run that regression and predict its residuals, and that's going to play the role of y. That should be beta 2 hat. Okay. Another way of, I can simplify this a little bit. I can simplify this by saying, okay, m1 x2 transpose equals x2 transpose m1 transpose m1 x2 inverse and I can simplify this as well by saying x2 transpose m1 transpose m1y. m1 transpose equals m1. We proved that earlier in today's lecture. So this is going to be x2 m1 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 x2 inverse x2 transpose m1 m1y. And as we also learned in today's lecture, x is idempotent. So can we go down? Add some more space. There we go. M is idempotent, and M1 is idempotent. Any projection matrix of the residuals is idempotent. So furthermore, we can write this as x2 m1 x2 or x2 I'm sorry x2 transpose m1 x2 inverse x2 transpose m1y. Okay, so that is our estimate of beta 2 hat from this second regression. Now what I want to show is that the estimate of beta 2 I get from running this crazy residuals regression, this beta 2 estimate here, is going to be the same as the beta 2 estimate I would get if I just ran, a normal person regression. And if I ran a normal person regression, so this is the regression I get from running these residuals on these other residuals. Now suppose I ran the normal person regression LMY on the whole thing of x. If I did that, what I'd get is, or what I'd be doing, rather, is the following. I'd be doing, okay, y equals pxy plus mxy, right? So this is y hat, and this is u hat, so that's just a simple identity. And that would give us, I could partition this out as x1 beta 1 hat plus x2 beta 2 hat plus mxy. Now, these are actually matrices. Okay, so what I mean by that, whoops, no. There we go. What I mean by that is this is n by k1. This is n by k2. So I've got like two mini, I've got two partition matrices here that I've broken up. So now I can rewrite this as, what can I rewrite this as? Oh, okay. x2 transpose m1 y equals x2 transpose m1 x1 beta 1 hat plus x2 transpose m1 x2 beta 2 hat plus x2 transpose m1 mx y. So what I've done here is I have pre-multiplied by x2 transpose m1. Now I can start to simplify things. For example, I can simplify something right here. I can use a theorem which we just proved a second ago, or which actually I'm leaving part of that proof to you in the homeworks, but this here is going to give me mx. That simplifies to mx. I can simplify this to 0 because m1 x1 is the portion of x1 not representable in x1, which is to say none of it. So this is just going to die. And so what I'm going to have left is x2 transpose m1y equals x2 transpose m1 x2 beta 2 hat plus x2 m or transpose m1 y. Okay. Now, I apologize. That should actually be x2 m. Oops. Come here, you. x2 mxy. Okay. Now, I can simplify this a little bit. I can say this thing here is like mx x2 transpose y. Well, what's mx x2 transpose? What is that? This thing is equal to 0. It's that what portion of x2 is not representable on x? Well, it has to be none of it, right? So what that means is that this here equals 0, so this whole term equals 0, so I can just kill that whole term. So now I'm down to x2 transpose m1y equals x2 transpose m1 x2 beta 2 hat. Okay, now what I'm going to do is pre-multiply by this. So I'm going to say x2 transpose m1 x2, I'm sorry, I'm going to pre-multiply by the inverse of that. That's a very important difference. x2 transpose m1y equals beta 2 hat. Well, what is this? Probably asking yourself that right now. What is this? That is the exact formula we derived for beta 2 from this residual regression. That and that are the same. Proof complete. I can run this crazy residual regression and get the same answer I would get through a normal person just putting all the variables in style regression. Which is an interesting fact in and of itself, I guess, if you're a nerd. But it turns out that it has very important implications for, I'm not going to say non-nerds, but lesser nerds who are more interested in data analysis. Okay, so I've just promised you that all that proof is actually getting us somewhere, and now I've got to deliver on that. So why is the FWL theorem important? Well, the FWL theorem is important for a couple of reasons, and one of them is also an interesting way of showing a consequence of the FWL theorem. So point one I've got up here is that scatter plots can be created using a consequence of the FWL theorem that correct for spurious correlation. Everybody likes scatter plots, right? They're very visual. Everyone can see what they are, what they're doing. It's real nice. The only problem that scatter plot has is that, well, one of the problems, I guess, that a scatter plot has is that it doesn't have any way of correcting for spurious correlation if it exists. And so it can be misleading. This is one of the first lessons you probably learned in your lower level undergraduate statistics course. But via the amazing properties of the FWL theorem, we can construct a visually compelling scatter plot that actually looks good. So what I'm going to do here is take you through an example of this. So I'm going to create some variables. Let's see here. I'm going to start here in my R script. So I'm going to clear out what I've got. This is the remove command, clearing out everything that's in the memory. You just saw it all just disappeared. And I'm going to use this library called MVT-norm. MVT-norm is a library that allows you to draw variables or sample variables out of the multivariate normal distribution. And that's going to be relevant here because what I want to do is sample variables out of a distribution that's correlated, or that are correlated with each other. So, for example, I'm going to draw x here out of the multivariate normal distribution. I'm going to draw 200 samples. That's the 200 here. I want them to have mean 0, and I want them to have a correlation matrix, or a VCV matrix. We haven't talked about it yet, but you may have heard it from Drew. We're going to draw they're going to be correlated at 0.6. That's going to be their correlation. So this is the sigma correlation matrix of 0.6. And if I draw this distribution and then I plot the first column of x against the second column of x, you'll see that these two variables are indeed correlated. In fact, I think if I even say, what's the correlation of x1 and x2? Ah, look at that, it's about 0.6, just like we said. So, okay, now what I want to do, I'm going to bind a constant variable to x. And so now if I do ahead of this, the first few rows of x, you'll see I've got x1, x2, and then this constant vector. This is the constant term in a regression. What I'm going to do is I'm going to invent some betas. This is just some random betas I drew out of nowhere, my head. And I'm going to create a dependent variable that's x beta plus a normally distributed error term with standard deviation 1 and mean 0. Alright, so if I run a regression of y on the x matrix, what I should get is something like negative 3x1 plus 1x2 plus a half x3, which is, roughly speaking, what I get. That's good news. This is the constant term, x3. This is the second column of the matrix I drew. This is the first column of the matrix I drew. Everything's great. Alright, so I'm going to take that data and I'm going to just plot. Actually, I think I need to expand my plot a little bit here. I'm going to just plot the second variable, x2, against y. Okay? And then I'm going to put in a regression line for that. And I'm going to compare that to the known true regression line that I created out of this fake data set. So I know the real regression line should have a slope of 1 because I said it should be 1. I made up this data. I know it's 1. If I plot a line with a slope of 1 in here, that goes in the opposite direction. We have a problem. We have a scatter plot that's telling us that x2 is negatively related to y, when in actual fact it's positively related to y. That could be a problem. And this is the short version of why scatter plots are not such a good diagnostic tool in cases where you have strongly correlated independent variables with effects that go in different directions. You'll see in my beta matrix here, x1 has a negative impact on y, x2 has a positive impact on y. Well, what's happening here is because I'm not modeling the effect of x1, x2 is sucking up that negative correlation with x1, and bam, it's giving me this crazy line that's going in the wrong direction. So You might conclude, scatter plots look good, but they're misleading. Well, yeah, maybe, maybe not. We can create a FWL corrected scatter plot. So what I'm going to come in here and do is I'm going to say, all right, I am going to run a regression of y on x without the constant. Oh, I'm sorry. Take it back. Already did that. What I'm going to do is I'm going to extract all the rows of x and the first 3 columns. So if I do a head of z, I'm sorry, I have column 1 and column 3. So I've got x1 and the constant. I've extracted x2. x2 is no longer in this data set. So what I'm going to do is model y using x1 and the constant. Bam. I've just done that right there. This right here is a regression of y on x1 and the constant and not x2. Okay? Then I'm going to predict the y hats out of that and subtract the observed values of y, getting the residuals of that regression. So now I've got y.res, which is the residuals of that regression. Then what I'm going to do is that same exact process, except now I'm going to model x2 with x1 and the constant. So there's my linear model right there doing that. And then I'm going to predict the residuals from that regression right there and get x residuals. Okay? Then I'm going to run, this is where it gets nuts. Then I'm going to run a model of the y residuals I just created against the x residuals. Oh, I got to actually create those x residuals, don't I? Blam. Okay, now, what did I do? What have I got? Well, here's the beta estimate, 1.07, of the x residuals from the y on the y residuals. Well, notice that matches exactly the beta for x2 that I got out of my grand regression. The FWL theorem says that is not an accident. The fact that that beta comes out to be the same is by no means a mistake. Now I can use that information to create a really cool scatter plot. So, okay, watch this. So what I'm going to do is I'm going to create a scatter plot of the y residuals from that crazy process against the x residuals from that crazy process, and that's going to give me what I call a FWL corrected scatter plot. So this is this right here is x1, I'm sorry, this right here is x2 net of the influence of x1. This is y2, I'm sorry, is y net of the influence of x1 and the constant. If I put in a line corresponding to the beta coefficient I get out of a regression of these two against each other, it very closely matches the true value of the regression line that I get, that I created out of this fake data set. In other words, I know the right beta. This is very close to it. So what this FWL process really kind of enables you to do is to create scatter plots that are not misleading in the way that a raw scatter plot might be misleading in the presence of spurious correlation. This picture gives an analyst or a reader an accurate idea of how x2 and y regress against each other, or sort of look against each other, net of the influence of spurious correlates that might be messing up the process. It's a really nice technique for presenting analysis in a paper or journal article or something where you want to give a reader a real good intuition of sort of how this data is moving together, but you don't want to throw in a scatter plot that's kind of BS because you know that spurious correlation might or might not be moving things around in a misleading way. So this is a sort of really cool use of this theorem to create a product, namely the scatter plot, which I think is sort of of immediate recognizable value to a lay analyst. But that's not all. There's more. Another thing that the FWL theorem demonstrates for us is that standardizing variables by centering them, for example, around their mean or maybe dividing by the standard error, will not change our estimates of beta. We can, in other words, rescale our variables and not worry about that screwing up our regressions in any way. The key idea here is that demeaning or centering variables is equivalent to running regression of a variable against a constant, which is something we talked about in an earlier class. So, for example, if I want the mean of some variable y, the mean of a variable y, I can get that out of a regression of y against its constant. So it's the beta that comes out of y regressed against 1. So if I call I a vector of 1s, right, then I transpose I inverse I transpose y is mu y. So if I demean a variable, so if I construct a new variable y minus mu y, what I am in effect doing is running a regression of y against a constant and extracting the residuals from that regression. And what that tells me is if I run mi y equals mi x beta, I will get the same beta hats that I would get if I ran y equals x beta, if I didn't mean center the variables. So in other words, if I want to standardize variables in some way by subtracting their mean, centering them on 0, dividing by the standard deviation or whatever, I'm not going to have to worry too much about really screwing up these regressions, because the Frisch-Wall-Lavelle theorem says that those transformations are neutral with respect to beta. So that's kind of cool. All right, so that's the conclusion of the lecture. Hope you enjoyed it. What we'll do in class is go over some problems and questions related to this lecture as a group. I'll answer any questions you have about the lecture material first. We'll spend half an hour or whatever it takes to do that, maybe an hour. And then we'll spend the remainder of the time drilling in on some problems as a group and individually related to this material, and hopefully that'll provide an opportunity for you to check yourself and make sure that you achieved a good understanding of the material, and also enable us to broaden our understanding of enable you to broaden your understanding of the material a little bit. Thanks so much, and I will see you in class.